Hello, everyone. Thank you for attending to my talk. I want to talk about this hierarchical community detection in hierarchical stochastic blocking model. It most of the things that not most of it. The main thing that I use is from the first paper. What does bottom up with top down in the hierarchical community detection? And I use the second reference for the for the introduction material. It's some starting papers from this subject, so it is easier to understand the initial examples, and then goes to the hierarchical case. So what is the community detection? When we usually it starts with a network that we have a bunch of nodes and some edges between the nodes. And the goal is to, and we know that some of these nodes are more related to each other than the others. And the goal is to find this community in between the networks. When we have the left information, we want to detect the right one. Okay, to detect these communities, actually the question is similar to the clustering questions that we have in the machine learning, in unsupervised learning. And the question, and there is a lot of algorithm called the clustering algorithm that start with a set of points, and we have a notion of distance between the points. And the goal is to group the points into some number of the clusters, such that the points that are in the, okay, so this distance, if we are in the Euclidean space, could be the Euclidean distance between the points. But in the case like the image, the figure that I show, if we don't have we don't have distance between the point, and we have some other information like the connection between the points, we could use another notion for the distance. For example, we could define some notion of similarity between the communities. And for example, when we have network, the similarity could be based on the edge density between the communities. It means that when two groups are have more connecting edges in between, they are more similar to each other. So we have some notion of distance or similarity, and the goal is to find the find the cluster such that the points that are in the clusters are more close or similar to each other, and the member of different cluster are dissimilar or far from each other. Okay, so here in this step, there are a lot of algorithms that gives help to find these clusters. But one question that here we can ask is that if we have any method to compare these clusters to each other. And to answer this question, one way is to define some model, like some random graph, and look at this different algorithm of clustering on this model. That this model is nicely defined in the sense that we know that in the definition it gives up some community, some meaningful community, and then after that, we could apply our algorithm onto this on this model and try to compare them in the mathematical sense to understand mathematically which of them is better than the other. So here we have this question. Then, if it is possible that we establish theoretical guarantee on the performance of this clustering detection. And it started with introducing some model that contains some community. And one of these model is this a stochastic block model, which is a random graph with communities. How it define? We have this stochastic blocking model We have three parameters, N, P, and Q. N is the number of the nodes that we have. P is the relative size of the communities, the number of the nodes that it's related to the number of the nodes that we have at each community. K is the number of the communities. For example, here we have 4 communities. And we have some probabilities for connecting the nodes to each other. We have some nodes that are inside the communities that are the probabilities that appear in the diagonal of Q. And there are some probabilities for connecting the communities. So this model defines our model that contains some communities. And when we have algorithm, we apply our algorithm on this model. We know that this model doesn't fit all the clustering problems, but it's nicely defined. So it is reasonable to consider that our data is fit to this model, at least in some cases. And then, so this is the model that we suppose that our data are behaving like this, and then we go to the define algorithm and to check that if the algorithm works good on this data or not. Okay. So the question here is that when and how we can recover the cluster from the groups when we have this model. And with when we mean that for which Q and which the size of the things that can cause that we be able to recover the cluster depend on 2 parameters. One is the size of the cluster, and the other is the probability that we connect the communities to each other. Why? For example, if all the probabilities are similar, actually we don't have any communities, so it shouldn't be the case that it is possible to recover the communities from some algorithm. So the things that we are searching for is that for which P and Q we could say that the cluster are recovered for some algorithm. And okay, and this definition this defines when the number of the nodes tend to infinity. And after that, we proved that for which properties relate to P and Q, the clusters are can recover. Then we can search for some algorithm that can do that, can recover the cluster. The simplest examples in this stochastic blocking model is when we have just two communities, and the 2 communities are symmetries, we have the same probability to connect the point inside the cluster, inside the communities or cluster, and we have different probability for connecting the different communities. And the size of cluster also is the same, okay, here the reason that I put this is that we can see that which kind of condition could be reasonable that we have to be able to recover the communities. Because then if Q and P are equal, it should be the case that we could not detect the communities. So the reasonable condition that we need is that the Q be less than P at least, and there is enough edges between the two communities and inside the communities. And there is a theorem that, okay, so let me describe this. Okay, first, this is some historical works on this problem. At the beginning, when people defined this stochastic blocking model, they tried to define algorithm and check the efficiency of this algorithm and the speed of this algorithm to see that which algorithm are recovering the community. And then people found some necessary and sufficient condition for the case that if P and Q have this necessary and if the probabilities between the communities and inside the communities satisfy this property, in this case, they proved that the cluster can be detected. And with the other theorem that is in the left side shows that if the P and Q satisfy that problem, be in this form and satisfy this condition, they are recoverable, and we can recover the cluster. And between detection and recovering the communities, there are some difference. When we detect means that we could introduce some algorithm that work better than uniformly assigning some label to one of the to each node, because each node has we know that we have two communities, one or two. So one way is to uniformly, for each node, we uniformly detect we uniformly attach one label, one or two. In this case, we have this 1/2 distance. This x hat is the label of the nodes that we assign. Xn is the right label of the node. And the things that we want to have recovery is that the probability that these two be equal when n goes to infinity be exactly one. Almost all the labels are correct when n goes to infinity. And detection is just some algorithm that is better than uniformly assigning some label. It's better than 1/2 minus. Okay. So the theorem that exists for this simple case, for this symmetry case, is that if for detection, if we have this property for the probabilities, we could detect the communities, and if we have the other the left condition, we could recover the community. And this part of the equation inequality shows that the number of the edges that we should have enough edges between the communities. This A plus B divided by 2 is the expectation of the number of the edges that we have between two nodes. It should be more than 1, so we have big enough communities, and it should be more than that to have to be able to recover the cluster. So the type of the questions, and after that we prove, the people prove that some model is with some condition is we can detect that or we can recover that. The people started to introduce the algorithms that can do this for each example. So for these two bound, we have efficient algorithm also. So the type of the question that we have in this model is that we define some model and we searching for some condition for the probability between the clusters or between the nodes and the communities, such that we can prove mathematically that the communities are detectable or recoverable. So there is one the things that the main paper that I want to talk about now, this is for the cases that the communities have some hierarchical properties, in the sense that we have different level of clustering, that in the initial level the nodes are more close to each other. And when we go to the further level, the distance, still we have some meaningful communities, but the distances are increasing between the communities. So we have some structure like the one that we see here. And we wanted to answer the same question as the previous one about these communities. That it means that if we can, in which cases we can say that these hierarchical communities are recoverable or detectable, and if we can introduce some algorithm that efficiently recover this community, the community like this. So for recovering hierarchical communities, the first step is to have some hierarchical clustering. So there are a lot of hierarchical clustering algorithms also in the literature, but we can divide it all of them in two methods, two general methods. One of them is divisive top down. That it means that it's which one? Is this one top down? Yes, it's this one. At the first level, we put all the nodes into one cluster. Then we started to divide each the cluster into sub cluster, and we continue this dividing. We could continue up to the time that we have reasonable condition to stop. And the second category is bottom top agglomerative. That initially, in this case, we start with putting each node into in its own cluster. Each node is one cluster, and then we have some rules to merge the cluster to create new cluster, and we could continue it up to the time that all the points are belonging to the same cluster. Okay, here maybe here now I want to just introduce some agglomerative perspective of this community detection. In the literature there are many algorithms that are divisive, but there is some point about divisive algorithm, and the point is that when in divisive algorithm because at the beginning we consider all the point and all the connection between the nodes, but then we started to divide them, and we should look at each of these subcluster separately from the other. So if in the divisive case, if we go from the first step to second step, we don't care after that the edges that are between these two subclusters. So we lose some information. And this losing of the information causes some bad behavior. For example, it is not usually these algorithms are not stable. If we do something wrong at the first step, this wrong information goes to the other step. Yes. So usually the threshold that agglomerative algorithm gives us are better than the divisive one. We could show the hierarchical clustering with some tree which is rooted usually. Each of the points that we see in the bottom of the tree are usually you could consider that each of them are the nodes of the communities, or sometimes the people don't do it, and they start with some, they perform some clustering algorithm, and they have some initial communities, and then they start to perform hierarchical clustering. So this leaf could be nodes or some initial communities, primitive communities, and then we connect when we connect the communities or nodes, we have some connection in the tree. And usually the height of the tree shows that at which level the points are combining. Okay, and we have we could see the difference between these two methods here. Okay, now I want to define the agglomerative algorithm that is introduced in the paper. That is very easy algorithm, the easiest algorithm that you could consider. The point is that we suppose that our model is a network. We have a graph with node with some edges, and the distance we want to define the similarity between the clusters or groups, the edge density between the groups. How we do this? We have a graph which is undirected. The nodes are V. The connection between the nodes are E. We have n nodes. Aij is adjacency matrix, and which gives the connection between the nodes. And this formula defines the edge density between the two set of nodes. It means that we look at we have two set of nodes, V1 and V2. We look at the number of the edges that we have between these two sets, and we divide it with the number of the sets. So it's the definition. And here you could see that if we start with some primitive clusters, and at some steps we have two subclusters. For example, C hat core1 and C hat core2. Then if we merge these two clusters and we recompute the distance between this new cluster, which is the cluster of core1 union of core2, this node, with other clusters that we have. Actually, this is some average between the distance, some average between the distance of the each of the clusters with the previous cluster. So when we merge, this equation shows that when we merge two clusters at some step, the distance between this new cluster with other clusters are the average of the distance between the subcluster of this new cluster with the other cluster. So
Sayeh,
yes.
would you mind showing again the definition of the row function? I'm sorry, I missed it.
Yes. This one.
Yes. Okay.
It's just we have two set of nodes. We consider the edges between these two set of nodes. We count them and we divide this number with the size of each cluster. It's a relative number of the edge between two clusters.
Which is the maximal possible number of.
Yes, possible.
Oh.
Thank you.
So the fact that the new distance between the clusters is the average distance between the previous distance set help us to ensure that we don't have inversion in our clustering. Inversion means that when we cluster, what do we expect? When we cluster, we expect that when we are in the in the lower cluster, the distances between the nodes that are in the lower cluster are less than the distances between the cluster when we go higher. So if this is what we expected, but not with all the algorithm it happened. Sometimes it happened that this doesn't satisfy. In these cases, we say that we have inversion. But with this definition of the distance, which is very natural, we don't have this. We don't have inversion. So in the other paper, the same author use this property to understand that, because usually when we have the data, we have network, we don't know that if they are hierarchical or not. So the people use these properties to conclude that if the data are hierarchical or not. They perform some clustering algorithm on it like this, and they look at the distances between the clusters in the initial steps and the higher step. And if there are some inversion, they concluded that maybe the data communities are flat. We don't have hierarchy. So we have this problem.
Just to be sure that I follow. So here the fractions are between the cardinalities of the corresponding cluster.
Yes. Yeah. Okay. So this property doesn't hold, for example, for the top to bottom clustering, divisive clustering. This okay. So if we summarize the algorithm is like that. We have a graph. We have some. Usually, people don't start the clustering algorithm from the first steps because the speed of the algorithm. If we wanted to use the same algorithm, the speed of algorithm is too slow. So first they started with they perform some flat clustering algorithms. They have some primitive communities, which are C1 hat to CK hat. And then they started to perform the clustering algorithm from this initial communities. So if the number of the communities is K hat, we start to, we compute the distance between any two clusters, and we find the ones that have they have the maximum similarity. We merge them, we compute new distances, and we define new clusters, and we do the same, and we continue this procedure. Here, so with this algorithm, we recover the communities plus the trees. So we have both. Okay, now we have the clustering algorithm. Like the previous cases, we wanted to understand how this algorithm works, and in which cases, if we have hidden clustering communities in our data, we can recover the communities. So again, we define some model that contains some hierarchical communities, and which is random, and we try to prove that in which cases this model is recoverable and in which cases this model is detectable. So this model this time is hierarchical stochastic blocking model. It's similar to the previous one, but it can, because the previous one doesn't contain, we had different communities, but the communities that doesn't contain hierarchy. This one contains hierarchy also. So now we don't need the algorithm. We are defining the model that contains hierarchical communities. And okay, here I need the board because there are many nodes. Well, maybe I could say, yeah, okay, I try to say the notation, but maybe it is not that needed. Okay, and we have, I could, okay. Maybe if I write here, the people could see.
On the screen,
on the screen. How are you?
It's just the screen of the projector here.
Yeah, on the screen of the computer, we see really well the notations.
Okay. What should I do then? I just want to, but I stop resharing, you mean? What should
I don't think it is a problem of sharing. It's a problem of the projector that is used to here in the
Okay. Let me. I try to just define the notation. Oh, suppose I want to just say that what we expected from the model that we are defining. We need some. We should have some trees. These trees should have. Maybe I have some. Oh, okay. Maybe I have one picture at least. We have. Look at the left picture. We need some things like this. we have some tree. It has different level. The first level we started from. It is rooted tree, so we have a starting point. This starting point first is empty set. Then we go to the other nodes of the tree. That if we go to the left, we have 0. If we go to the right, we have 1. So we have some label for each node. And we could continue up to the time that we reach the this primitive communities. So the things that we expected is that first, when we should when we in the bottom level we have different communities. We should define how we wanted to connect each node in the each node that we have in our data is belong to one of these primitive communities. We should define that how we want to connect each node to the other node, and we define this with the lowest common ancestor between two nodes. Why? Because when they are in, lower, we want to have a hierarchy. When they are in the lower levels of the trees, it shows that they are merging sooner, so they are more related to each other. So the probability that they connect to each other should be higher. So we look at the first for each two nodes. We look at the first time that they meet each other. And based on that, we define some probability that they connect to each other. When they are low, we define the probability first. When the nodes that are lower have more probability, when we go up, the probability decrease. So it's and also we need to the other point that we need to have is that this probability shouldn't be to really we have this hierarchy. The probability should be decreasing, for example, fast enough. We should have some condition like that. So the definition, I think I told anything, this definition, oh yes. So we have n, which is the number of the nodes. We have a tree, which is rooted. LT is the number of the leaves, which are the primitive communities. We have some probability that these probabilities are relative. They are just relative size of the primitive community, because they are. We know that primitive communities are not the same. Could be not necessarily are same, and they are not only single point. We have primitive communities. So we have this function P that defines some probability on the nodes, and this probability should be defined such that when V is a child of U, the probability of U is less than probability of V. When we are lower, the probabilities are higher. When we go up, the probability is less. So in this case, we have a hierarchical stochastic. This definition is definition of hierarchical stochastic block model. Okay, what is this? Yes, and we know that each node is assigned to one community, and yes, the probability of the connecting each node from community A to each node from community B is related to the first lowest common ancestor of these 2 points. I told this. So this is the definition. So we have some graph, some tree like this. And in the right one is the simplest case that we have binary trees, that the probability of the everything is very symmetry at each level. All the P are at one level, all the P are the same, and it's like that. But it could be like the left one. Again, I need to write. Okay. Here.
Sayeh,
Yes.
could you explain more precisely what in the binary case, what P3, P2, P1, and P0 are? Just
this okay. We are in the binary case, so the size of each of the communities are the same, for example.
Yeah.
And each two, the common, look at it, for example, in these two communities. The common ancestor of these two are this one. And the common ancestor of these two is this one. And these two clusters are exactly similar. So the probability that we should define to connect these two communities should be the same as the probability that we should define for these two. And it is for all the case, it is true for all the, because in the binary case, we have, for example, 2 nodes, 8 nodes. First, every 2 nodes are connected. Then we have another branch that 2 clusters with 4 nodes are connecting, and they are the same. So the probability that they connect to the adjacent cluster is the same to each other. And then it's the same for the next level. Also, we have exactly the symmetry. So we again we have the same probability to connect the subclusters and all of that. Because it is symmetry. When 2 clusters at each level are connected, the probability that they connect is the same with the other two.
Okay, I get it. And so now the PIs, this is the parameters in the model. Like the P and the Q earlier in the 2 blocks.
Yes, exactly. But there we only had one P and Q.
Yes.
Here we have a level of P of Q that they are
a tree. Okay, a level. Yeah, P0, yes. P1, and they are given by the model. The model
yes, they are given by the model. It's the definition of the model.
Thank you.
And the only point is that we know that the probabilities are decreasing. Because the probability that they merge at the first level it should be higher than the second level, and it should be higher than the third level.
Okay. Thank you. And if you are given this model, then you can produce a sort of extended Erdős-Rényi graph, which will have this hierarchy of connections, right?
Yes, but you should note that in the Erdős-Rényi we don't have hierarchy. So
right. The hierarchical Erdős-Rényi, whatever, right?
Yes,
you can build a sample of it, right? Okay. Thank you. Yeah, thanks.
Correct in saying that the first stochastic block model would correspond here with a tree with only 2 leaves.
Yes.
And Erdős-Rényi will be only the previous tree with 1 leaf.
Yes, exactly. It's flat. It's the case that we say that it is flat. It means that it's the case that I thought that this edges doesn't show any difference if you count the distance between the comments. So okay, I wanted to prove this part on the board, but we don't have board. So it's okay. In the next step, the thing, okay, we have the model. We should answer this question that for which P and Q or which set of P, the model is recoverable or detectable. The point is that if we have suppose that we have this model, when we have 2 clusters, two communities, the number of the number of the edges that we have between these 2 communities is has binomial distribution. So the expectations of the number of the edges that are in between these 2 communities is equal to the size of the first cluster times the size of the second cluster times the probability that we connect these 2 clusters to each other. So if I put some condition that the number of the edges that I see between these 2 clusters concentrate around this expectation, in this case, we can show that the similarity, if I compute with, I introduce some algorithm. If I put some condition that the number of the cluster have this property that concentrate on the expectation, and if I compute in this case this similarity, it means that in the numerator we have the size of V1, size of V2 times the probability that V1 is connected to V2. So the similarity of V1 and V2 is corresponding to the probability that we connect V1 to V2. So this algorithm, it shows that if the primitive cluster already are detecting exactly, then the hierarchy with this algorithm detecting exactly, almost exactly. So the condition that we need, okay, I wrote the theorem, I wrote it. Okay, so if we consider the hierarchical stochastic block model with the, but that contains this tree and this co-leaves, which are the co-primitive communities, and we have the good conditions on the probability that we connect the communities to each other in the sense that they are proportion to something, that they are big enough. They are not too big, they are not too small, in the sense that this property holds that the expectation of the number of the connected edges are near to the expectation. The distribution of the connecting edges is near to the expectation. In this case, the algorithm recover the almost exact recover the community. So we have this this property. So the condition actually is this. This is this one. We need this condition. Yes, it's for but it is for there are other. It's one of the theorem that they in this paper that it gives some condition for almost exact recovery. There is other condition that it gives the exact recovery, but it is not possible to exactly recover all the depth of the algorithm. But there are some conditions to put on some level to exactly recover that level.
Excuse me, Sayeh. In the notation, P of t is equal to A of t delta n. What does delta n means?
Delta, it's the problem. Because here I should put some. Here is the condition that we put for the probability. We have some constant, and it should be big enough to give some good condition. Yes. Yes.
But delta n, what it means here?
It should be defined. It means that it's something that it is related to n. It's just that.
Okay.
It's the order of the probability. We should put some order for the probability, and this order is by the given by.
Okay, it's just a sequence.
The order is 1 over n2 or something like that.
Okay.
And additional question. So this is an extension of the symmetric, not the symmetric.
Sorry, the definition is.
And so,
delta n is of order 1 over n.
Sorry, yes.
Yeah. So, and how is it connected, for instance, to the earlier result? If there is no hierarchy, but just one level, then so it should be connected to the threshold that you mentioned.
The first one, no, the similarity is just that they put some condition on the probability, and the probability shouldn't be too small. We should have some large component in something. In both of them, the intuition are the same. When the time that we can detect the community, I wanted just to give the intuition. Because of that I defined the first one. When the communities are recoverable, when we have enough edges between the clusters, and this to satisfy this, we need to put some condition on the probability.
Okay, and so the shape of the A function is the analog of the conditions that you mentioned at the beginning.
Yes.
Right.
The
okay,
type.
That's
yes, exactly.
The shape of the A function. Okay. Okay. Thank you.
You're welcome. Okay. Yeah, I think I should finish there. Yeah, because I don't have any other. No. Okay. Thank you.
Are there some more questions
Yes,
on the bridge or in the room?
Perhaps I have a couple of questions. I mean, or at least one central. I mean, so it seems that so community detection exists under two brands. The Erdős-Rényi brand, which is fundamentally spectral, and the Euclidean one. And so can one devise, I mean, because the one that you mentioned is purely the Erdős-Rényi. There is an edge or no edge, right?
Yes.
But you could, yeah, you could replace that by edges which are function of distance in the Euclidean case,
Yeah,
right?
I think it's just the point is the algorithm here is not that important, because this algorithm is I defined my algorithm based on the edges, because I suppose that I have some nodes and the only information that I have are edges. I don't have anything.
Okay.
If I have these things, I could change it. I could change the definition from the density of the now it's based on the density of the edges. It could be based on the
distance. Yeah.
It's
Okay.
okay. Yes, it doesn't affect the recoverability and detections of the communities. It is just one, because after that we tell that we can recover the algorithm, the communities. We should introduce some algorithm that recover it.
Yeah.
For these cases that we have the nodes and the edges, the algorithm that work is here. But I think if we have distances, it should be the same, because it is not that difficult to prove this one also.
Yes, but I mean the point is that of my question is that I mean the thresholds and the concepts are completely different when we move to Euclidean, right?
Yes.
And therefore, if you devise and define a hierarchical geometric stochastic block model, you may expect that the conditions on the A function for either recovery or detection will also change, because we know they change dramatically, even if there are only two communities, right?
Yes, exactly.
Okay.
The size and the distances, it should be, I think that instead of the density, some threshold on the density, we should have some threshold on the distance between the classes.
Yes. Yeah, or the difference of, right. Okay.
Yes.
And so currently, did anybody devise the notion of say, what should you call it, geometric hierarchical stochastic block model? Was it discussed anywhere?
No, I didn't see that. I just
okay, good. So we have to invent it.
Always because they consider it usually they consider it on the networks, and they suppose that we have, even when they define with the edges. But I think it should be, yes.
Okay. Okay, that was my question. Thank you.
Thank you.
Other questions? François, you had other ones, or?
You have the other one?
No, because it was linked to the Euclidean extension. And so no, perhaps one. I mean, if you take the purely the tree that you mentioned, the binary tree, right, or DRE tree, does one know the A function?
I don't know.
Okay,
I don't know that because I don't know that. I think that the only paper that I could find for this hierarchical, this bottom-up hierarchical, is this paper.
Okay.
So I don't know that I don't know. I'm not sure that there is other result about that. In this paper, they only show that there is a threshold for the exact threshold, the threshold for exact recovery, for almost exact recovery. They have some numerical result, and that's it. And we compare this one with the top to bottom case, that this one is better than the only thing that they mentioned in this paper is this.
And so, okay, so they show that there exists a threshold, but if I understand your answer is that they do not provide the exact value of the threshold, like the closed form formula given in the
threshold. They told that exact value. What do you mean?
Well, in the earlier stages when you summarize the paper of Sayeh and others, you say if A minus B is less than whatever, and it was if and only if.
Here also, it is not if I, no, here it is not if I only if. They just showed that the algorithm recover the almost the exact recover the model.
Okay. They give sufficient condition for A
To be
to
recovered
recover
with this algorithm.
with
Maybe
this
there are,
algorithm.
yes,
Okay.
maybe there are other algorithms with better threshold that recover better. It is not in if and only. It is.
Oh, okay, okay, okay. And but if the tree is given to you together with the P, is there is a closed form expression for the A of T function or not? For the sufficient condition.
It is this one here. When the probability should be proportional to omega 1 over n. Over n, oh yes.
Yes, but I mean, I think this is the scaling that you had earlier, that everything was in 1 over n. But there should be something on the A function, if I get it correctly. I mean, earlier.
Is the probability, it's on the probabilities, no? Here we have probabilities, this delta is related, these are probabilities.
Okay.
A are some constant, and we have this value delta n. This delta n has this properties. If this delta n has this properties, it means that we put some condition on the probability. So with this condition, we have the sufficient condition. It means that the probability between communities should be a bit more than 1 over n.
Okay.
It is 1 over n2. I don't know why here. I think it's just 1 over n2. I don't know why here. I think it is some typo here. But it is no, it is 1 over n. No, it's true.
Because this is for this is not for recovery. This is for detection, no?
It's for
This is for detection or recovery. This one.
Recovery. It's for recovery. It's almost exact recovery. It is not exact recovery. It's almost exact.
Okay. Thank you.
Okay.